This is the first video of a new series I'm going to be doing on some work I've done on the evolution of consciousness. My work tends to have a mathematical approach to various topics regarding the relationship of mental and physical systems. In this particular series, I'm going to be addressing the conditions that would allow for the evolution of qualitative subjective experience. The topics explored in this video are going to be largely summary, so I'm going to be following up each of the major topics with a video of its own. And so as I walk through, I hope to give an idea of the general trajectory of the work that I've done, as well as some of the overall results, but further detail will follow in the videos that will be coming. For any of you who are interested in reading the papers themselves, I'll be posting a link in the description. So I'm going to start off with a quick outline of the three primary results of this work. The first is that any correlation between domains will convey a selective pressure between them. Now you can think of the domains as being the physical and mental domains. In the course of the talk, we'll slightly sharpen those notions, but those are good enough for now. So the key here is that any correlation between domains will convey a selective pressure. So what that means is that there's no causal requirement in order for a selective pressure on one domain, let's say the physical domain, to be conveyed over into a mental domain. All that's required is that there's some correlation between them. The second result is that this selective pressure can only be efficacious under specific conditions of a minimal fidelity between the systems. And what that means is that that correlation between the domains, if it's anything less than perfect, it will dampen the selective effect to where past a certain threshold, the effects of random mutation and other noise in the evolutionary signal will get dampened out by the lack of fidelity between the systems. And so what ends up happening is that you can have a selective pressure in, say, the physical domain that doesn't effectively translate over into any coherent result in the mental domain. And there's a precise bound on this that we'll see that I call the qualitative selection limit. And the third result is that as important as this fidelity between domains is, just as important is the fidelity between different levels within the same domain. So between, say, the level of fundamental physics, whatever that might be, say, subatomic particles or fields, up to organisms, that translation between domains introduces noise of its own that has to be accounted for in that fidelity that I was speaking about in the second point as well. So taking a look at the exact relationship of the higher level systems to lower level systems is just as important as looking at the translation between domains. So this is a statement of the general question that sparked the inquiry. Even if we take it as given that the world is somehow possessed of an essentially qualitative character, why should that qualitative character manifest in a way that is functionally relevant for higher organisms? So essentially, it's largely taken for granted that qualitative experience has been selected for by natural selection because it has been functionally relevant for organisms in some way. And when I started to think about this, it opens up a host of questions that haven't been addressed. What role would it play for the organism to have qualitative experience? And does it need to have causal efficacy to be selected for? This is the core difficulty. On some level, any functional description won't account for its qualitative nature, because as soon as you've given the functional description, you're describing the aspects of that property that are no longer qualitative. So I take the qualitative properties to be things that are sort of ineffable, like, your sensation of red or the smell of coffee, etc. You could easily imagine those sensations to be otherwise in their quality, and yet they would fulfill the same function for you as an organism. The core difficulty becomes giving an account of why exactly the qualitative nature comes along the ride for any functional description, because it always seems to be a passenger. This line of thinking gives rise to a further question of why do the qualitative properties align with the functional properties, and especially at higher levels. There doesn't seem to be any a priori reason why qualitative properties should be in line with the functional needs of an organism. I mean, certainly if there was some connection at a fundamental level of the world, like let's just say, for example, that every up quark was like red and every down quark was blue, and you went through each of the subatomic particles and gave them each a color. Well, there doesn't seem to be any apparent reason why those colors would manifest in any recognizable shapes when you're looking at a large system of them. They're just obeying the dynamics of fundamental physics. It is quite a puzzle why at higher levels, even if there was on a fundamental level some kind of a connection between mental and physical systems, how that cascades up to higher order systems. And so in my general inquiry, what I've done is I've laid a framework that allows for at least approaching these questions, and in some cases giving mathematical bounds and conditions on the types of systems that would allow for natural selection to be conveyed. And I've proposed a new framework for approaching the dichotomy between these structural and qualitative properties, as I call them, that gives us clarity not only into the potential evolutionary history or selective pressures that would have led to qualitative subjective experience in biological organisms, but also I think gains us some insight into what's called the hard problem or the mind-body problem, not in the way of answering the question, but actually posing it as a separate question. So here on this slide I say, with a simple framework and known evolutionary theory, we can derive mathematical constraints on the relationship of body and mind. And so that's my essential thesis, or for what I'm going to be going through in not only in this video here, where I'll be showing the general trajectory of the work, but then in each subsequent video I'll be touching on each of the topics that I mentioned in more detail. So here I'm going to set that dichotomy, like I mentioned before, not between mental and physical things, but between structural and qualitative properties. Structure is the things that are related to function, relations, things that can be described abstractly, whether that's in an equation or even in a description. They're things that can be conveyed even if you never had any immediate subjective experience of something. Quality is the ineffable and intrinsic, something that can only be referred to, meaning you have to be or have the property in order to grasp its essence. The classic example would be, somebody who is born blind will never understand what is meant by a color. It's just not a modality that they're familiar with, that they could ever attach the qualitative, ineffable, intrinsic aspect of what it is to have a color, because that aspect of experience is not available to them. So the essential idea of breaking it down in this way is an alternative way of splitting things up as opposed to physical and mental. Because I think both the categories of physical and mental, they come along with a lot of baggage, conceptual baggage. Some of it is obvious and some of it is not. And so I think it's better to take a step back and realize that the reason that the physical and mental ultimately seem to be in some way incongruent is because of the fact that they are seen as primarily having structural properties, which would be the case in the physical. That notion itself is largely given based off of our ideas of how we study physics. We give equations, we describe relationships between quantities, and it gives us a picture of the physical world, quote unquote, as being one that is entirely structural. On the other hand, the qualitative, what are often called qualia, I don't have a particular objection to the term qualia, but I do avoid using it because I think in the same way that using the terms physical and mental brings along a lot of extra baggage, I prefer to use a more general term like quality or qualitative properties, because I think it's a little bit deeper than what would ultimately be considered qualia in all instances. So I think that there are likely certain aspects of existence themselves that are not amenable to description in terms of an abstract equation or visual representation of some sort or some relational characterization. Something intrinsic that is ineffable and undescribable, the difference between an actual existence in the world of something and something that is just described in an equation. So it's very much along the question that Stephen Hawking asked about what breathes fire into the equations. Now, one thing with this dichotomy is that it sets what's called the hard problem or the mind-body problem on a completely different basis, because I believe that that structural and qualitative properties are sort of, by their very nature and the way that we consider them, they're in some ways two sides of the same coin, but they're never resolvable to each other. I would say that structural properties are, by their nature, they're relationships between things. They can inherently be described abstractly because the relationship does not need to come along with the relata, the things that are being related. The relationship can be divorced from the things which make it up. On the other hand, qualitative properties are intrinsic. They're properties of the thing that is itself in the world, whatever that might be. Whether we colloquially call it the charge of a particle, or we call it the sensation of red, or we colloquially call it the smell of coffee. These things are all not reducible to simple descriptions in terms of relationships of things, and instead have to be, in some sense, present to us firsthand in order to fully grasp exactly what's meant by them. So I think ultimately the hard problem of consciousness is actually arisen from a more fundamental disparity between structural and qualitative properties. But notice, if we change our thinking about this from being a dichotomy between physical and mental properties, it opens the door to other alternatives for the relationship between mind and body than are just available to us if we take mind and body as a simple dichotomy. And in the course of the videos that will come, when I talk about the categorization that is put on offer for different metaphysical systems, idealism, physicalism, panpsychism, different ideas about the fundamental relationship between the mind and the physical world, it allows us to put in place a more principled categorization of those systems that's based on more fundamental relationships between structure and quality. So, comparing structure and quality, we're just going to take it as given that qualitative properties can't be captured by any linguistic or formal description. And I think that that's actually a very common thing even in other sciences. What we do is we adopt symbols that stand in for actual existent entities. In Newton's second law, F equals ma, m stands for some actual qualitative mass that exists somewhere, and a is an actual acceleration of that. The quantitative measurements that we apply to each of those quantities is in no way a stand-in for the actual existent object itself. And so, even though this might be operationally the way that we go about finding out and laying out what these qualitative properties are is different than it is when we take the third-person point of view and we do it in the realm of quote-unquote physical objects, I think ultimately the process that we're undergoing is the same. And so, in the same way that in the hard sciences we offer descriptions of systems and their connections and relations to each other, but we never ultimately define formally what the objects are. We might speak about what we're talking about, but really what we're doing is just honing down referential language so that other people who have encountered these things understand what we're talking about. But ultimately, when we propose a new physical law or a law in any of the hard sciences, what we're doing is we're offering a description of some regularities within a particular system or a class of systems. And so the same on our end, what we're going to do is we're going to take it for granted that qualitative properties exist and that they can't be captured by any linguistic or formal description, but they can be referred to, of course. And then we're going to offer descriptions of all of the possible connections between qualitative and property and structural properties of a system. So looking to formalize and make more precise what the relationships between qualitative and structural domains are, domains is what I usually call them. The first step that we need to do is formalize the separation. So all that we're going to do is we're just going to say that the structural domain, we'll call it S, and the qualitative domain, we'll call it Q. So S is the domain of all properties that can be described entirely via abstract relations, and Q is going to have some formal structure in order that we can map it to the structural domain, but ultimately Q will be the domain that refers to these qualitative aspects of reality, whether that's a scent or a color or some other ineffable quality of the world. So the first thing we need to ask is, what are the possible relationships between them? If we're going to try to determine which ones are feasible, we want to look at all the different possible relationships. And it turns out that there are actually 5 of these. The first is a bare functional relationship. It only consists of S, and it denies the existence of Q. This is a view something like computationalism or functionalism in the philosophy of mind, or in the ideas of a it-from-bit physics that takes the underlying stuff of the physical world to be some sort of quote-unquote pure information. So what these systems do is they say all there are relational properties, and there are no qualitative properties. The second approach is to say that the system is structurally determined. So what this means is that you can state everything that happens within S, and you can, if you knew everything about S and you knew all the laws that governed S, you could evolve S forward in time and it would unfold, and you wouldn't need to know anything about Q in order to be able to predict the continual behavior of S over time. However, this view is unlike the bare functional view in that it has a mapping from each state in S to a state in Q. And so it doesn't deny the reality of a qualitative domain. It just places it as in some way secondary or a readout of the evolving state of S. And so you might think of this as a sort of epiphenomenal view, and many versions of physicalism would fall into this sort of camp. In a separate video that I'll be doing involving these possible relationships between qualitative and structural domains, I'll be touching more on the interpretations of these different relationships in terms of what they're generally approached at in classical ontology or philosophy of mind, things like idealism, physicalism, different flavors thereof, etc. A qualitatively determined system evolves according to Q, and it has a mapping from Q to S. So this is basically the same as S, but in reverse, where it takes Q as the primary domain, and it takes its dynamics, the laws that govern its evolution, as being fundamental to Q, and then it has a mapping from Q to some structural domain that's secondary. A mixed determined system is one which evolves according to factors in both S and Q. And so you could never understand the evolution of either S or Q without understanding properties from both of them. And finally, an equivalent system is one which S can be fully determined by the knowledge of Q and vice versa. So this is one where there's sort of two sides of the same coin. In a later video, I'll be going through the exact formalization of these different dynamics, but I do believe that it constitutes, at least if you accept the initial distinction between the domains S and Q, I believe that these 5 possibilities cover the whole space of possible relationships between the two domains. And I'm open to other ideas. I could be wrong about that. It could be that the separation between two main domains, S and Q, is somehow posed incorrectly. But I think if you take the assumptions that we've had so far, this covers the entire space of possibilities. Now, one thing I'll just show you very quickly that we'll be coming back to in a future video is that I've actually illustrated each of these in terms of cellular automata models, mostly resembling or variations of the game of life. So for those of you who are unacquainted, cellular automata are systems of sort of pixels. They don't necessarily have to be discrete, meaning pixelated, and they don't necessarily have to be two-dimensional, but most commonly they're two-dimensional or one-dimensional and pixelated. And then there are just simple rules on how their behavior evolves. They tend to be of particular interest because through some simple rules you can observe complex emergent behavior. But the reason that I use these systems as models for Q and S is because they're very simple, and conceptually they allow for very clear models of the 5 possible relationships. So in these models, what I basically do is the pattern on the grid generally represents the structure, and the colors that are laid on top represent the qualitative properties. And so obviously in the real world, the structural domain is much richer than a grid, and a two-dimensional grid, and the qualitative domain is much richer than just the set of colors that the human eye can discern. But just to walk through the basic idea of this, so in bare functionalism, there's just black and white, so these are sort of just abstract on and off states, and there are no qualitative properties, and there are simple rules how this system evolves. In the second system, the rules for how it evolves are exactly the same as in the bare functional system. But there is an additional rule that assigns a color to each pixel based off of, essentially, in this picture, the concentration of the number of pixels that are active within some radius of that pixel. And so the evolution of the system is completely structurally determined, but there are additional laws that determine its qualitative properties based on the structural state of the system. In a qualitatively determined system, there are different colors of cells which are intrinsically different, and the rules for how each cell behaves is determined by its color. And so a blue cell behaves differently from a white cell, from a black cell, from a yellow cell. This is a system whose dynamic behavior over time depends directly on its qualitative properties. And then finally, there's an equivalently determined system, which these look like gray blobs, but they're actually a variety of different shades of colors. And each one of these colors actually maps to a specific state that you might see in a sort of black and white picture. And it can be decoded, each colored cell can be decoded into a neighborhood of the state of not only that individual cell, but the other cells around it. And what that allows you to do is to equivalently state the dynamics both in terms of transitions between different colors of cells, which is completely deterministic and one-to-one, and the underlying structural description of the system, which is basically a grid of active and inactive cells. And so the dynamics that you can define structurally and the dynamics that you can define qualitatively are entirely equivalent and can be translated back and forth between each other. So now that we've discussed the possible relationships between structural and qualitative domains, it will be useful to introduce a similarity measure between those systems. And we'll be putting it into use here shortly. But in and of itself, it has some interest. So the question we ask is, how much does knowledge of S inform us about knowledge of Q? And of course, we can ask the same thing in reverse. Not only can we ask the same question in reverse, but it's asymmetric, so that the amount of knowledge we gain about Q from S may well be different than the amount of information about S we gain from knowledge of Q. So essentially, we need to express these similarity measures as a pair of two numbers, not just one, because there's one that will tell us in one direction from S to Q, and the other that will tell us in the other direction from Q to S. So we write these as two numbers with a little Q with this hat diacritic over it, and then alternatively with as an S with the hat diacritic. I just use the hat diacritic as notation to separate it apart from other uses of Q and S in the math, but it doesn't have any independent meaning outside of that. The type of QS relationship will inform the measure that we get. So in a structurally determined system, we'll have S equals 1, which these numbers are essentially normalized between 1 and 0. So you can think of them as percentages, where 1 is 100% and 0 is 0%. So 1 would mean that 100% of the information about the other domain is determined. And so the little S hat equals 1 there means knowledge of S will tell us 100% of the state of Q. So if you know the state of S, you can completely derive the state of Q. And alternatively, if we had Q hat equals 1, if we knew entirely the state of Q, we could derive the state of S. Alternatively, if we had S hat equals 0, that would mean we could know everything about the state of S, and we would know nothing about the state of Q. So we can lay out these pairs in sort of a simple space. You can think of this sort of like an XY chart from high school math, where instead of the X coordinate, we have the Q hat, and instead of the Y coordinate, we have the S hat. And remember, these are normalized between 0 and 1, so the maximum value of any of these is 1. But if you look at each of these coordinates, this basically shows you why the categorization that we came up with is exhaustive. It covers all the possibilities. And so the first bare functional type of system is one at 0, 0. So since there is no qualitative domain, there's nothing for S to tell us about Q, and there's nothing for Q to tell us about S. So that resides at the origin. Any coordinate that has S hat equals 1, so that means this here on the axis, but also this entire line over to 1, 1 is a structural system. And that means that S hat equals 1, therefore if you have full knowledge of S, you can derive knowledge of Q. Vice versa for qualitative systems, if you have full knowledge of Q, you can determine S, and that follows this vertical line. The equivalent systems here have 1 for both S hat and Q hat and S hat, so that each one can be fully determined from the other. And a mixed system is any other point in the space that is not covered by these points and lines that are outlined here. So any other system that is not at either the origin or does not have one of their coordinates equal to 1 will be a mixed system, in which information about one will partially determine information about the other, but neither one fully determines the state of the other. So now we ask, how does selection on one domain influence the other? This is a key question, because this is how we understand what the role of the qualitative system is, or potential relationships of qualitative systems are in the context of natural selection, and can lead us possibly to favoring certain relationships over others. So here we discuss what I call the conveyance of selection. So that would be the idea of conveyance is if one of those domains is under a selective pressure, it will, if it has a relationship to the other domain, it will convey that selective pressure into the other domain. And so when we apply selective pressure on a domain, it reduces the set of possibilities within that domain. So here, if we look at the S domain over on the left, we see some white circles, and we'll just take it for these illustrations that the white circles indicate the organisms that have survived to reproduce, and the black ones have not. So what this ultimately is a reduction in the set of possibilities in the domain of S. Now each one of these organisms in the domain of S also has an equivalent manifestation in the qualitative domain, the domain of Q. But only the ones that are associated with those organisms in S that survived will carry on. And so here in Q, the black dots that have the dashed circles around them are the ones that have been selected and will perpetuate into the next generation. So one important thing to note is that the reduction of possibilities in the structural domain automatically leads to a reduction in possibilities in the qualitative domain. Now that doesn't tell us everything that we need to know, because there may not be any coherence between these two domains, and that's where our fidelity measures come in, as we'll see on the next slide. So we can have this idea of noisy conveyance, where if our fidelity between the domains, and in the examples that I'm going to be giving here, we're going to be looking at the idea of selection being applied on the structural domain and then being conveyed over into the qualitative domain. So you can essentially think of this as either a structurally determined system where S hat equals 1, or also as you could also think of it as an equivalently determined system. So this first scenario shows perfect conveyance from one system over into the other. So we have a set of the white circles in the structural domain, and they each map to a green circle in the qualitative domain. So knowledge of the set of items that have been selected in S gives you perfect knowledge of the ones that have been selected in Q, namely that they're all green. Now in the second picture, we have both green and blue qualitative manifestations that have been selected. And so roughly this is something like an S hat equals 0.5 system, where half of the variation is determined by the structural domain, and there's still half of the variation that is left unexplained. So you've only resolved half of your uncertainty by knowing that an entity has been selected. And finally, we have an uncorrelated system where S hat is equal to 0. And so in this case, we have one of the selective entities is green, one of them is blue, one of them is yellow, one of them is orange. And so knowledge that an entity has been selected tells us nothing about its qualitative manifestation. So keep in mind the consequences of this. What this means is that in this system here, the selection in the structural domain for the white circles has translated into a selection for green circles in the qualitative domain. In the second system, it's translated not just to a selection for green circles, but to green or blue circles. So you've narrowed down the selection. You haven't gotten it down to a deterministic relationship where there's only one possibility, but we have narrowed it down from 4 possibilities to 2. And then finally, in the last example, we've had no reduction in the uncertainty that you have. If you tell me that an organism has been selected for, it may have any of the qualitative manifestations. Now, a priori, or going into it without any other information, there's no reason to necessarily expect on the level of higher level organisms, even if you thought that on some fundamental level there was some correlation, like I mentioned at the beginning, between some sort of fundamental particles or fields and particular qualitative properties, even if you thought that on some fundamental level there was some correlation between these two, it's hard to see that in principle there would be a correlation between these two domains on the level of higher order organisms. And so we're going to be looking into that shortly. So, as I was getting at there, we saw that in noisier systems, down to where there's no correlation, you get to no conveyance of any selective pressure. If there's any correlation whatsoever, there's at least some reduction in the uncertainty in what you have in the qualitative domain. So if S hat is equal to 0.01, there's still some reduction in uncertainty in the distribution of qualities that will be selected for. It won't be very significant, but any correlation that we have between these two, if we produce a selective pressure on the S domain, that correlation will be translated over into the qualitative domain. However, there are more factors to take into account. So not only is there selection in the fidelity between the systems, but there's also mutation. And so even disregarding the effects of fidelity between the two domains, there is an equation in evolutionary biology that's called the price equation. And this term here is derived from the price equation. It's not the price equation itself. But essentially, the top term, and I'll be breaking this down in another video, but the top term here represents mutation. And the bottom term represents the selective pressure for a trait. And with the application of our fidelity, I was able to derive this specific inequality that says that if the ratio of mutation to selection is high, that begins to override the selective effect by mutation. And this is a natural effect that happens even without the fidelity. But now that we've introduced the fidelity, it's almost a separate set of noise, one that amplifies the mutation effect. So under normal circumstances, you would look at this ratio and say, if this ratio is much larger than 1, meaning mutation is much larger than selection, then the selective effect begins to be drowned out. In our case, it's less than 1. Now remember, fidelity is sort of like a percentage. It falls between 0 and 1. So what we're saying here is that it dampens the selective effect so that the ratio of mutation to selection can be much lower in proportion to the fidelity, and the selective effect on the qualitative domain will no longer carry over. Now, remember, I'm stating this all in terms of sort of a structurally determined system because it's sort of the picture that's assumed by most in the hard sciences. But this same sort of analysis applies to any given system. It just is easiest to assume one of the systems in order for illustration. So what we have here is a hard limit, quantitative limit on circumstances that need to hold for your proposed relationship between mental and physical systems in order for the selection on one domain to convey into the other. The assumed version of that in the hard sciences would be that there's a selective pressure in the structural domain that needs to be conveyed over into a qualitative domain, and therefore that the quantity S hat, the fidelity of Q as determined by S, is above a certain threshold. Now we have some simulation results here, which I won't go into all the details of here on this video, but the one that we're primarily interested in is this last scenario. Well, first I'll show you, in the case of ordinary natural selection, we have the yellow line, which represents fitness, which means how well adapted an organism is to an environment. S represents a structural property, and Q represents its qualitative analog once it's been translated into its related qualitative property. And you can see that these three all sort of work in tandem under normal natural selection, where the x-axis is the number of generations, and so as more generations unfold, natural selection has more opportunity to work. The key takeaway here is that as generations go on, there's a general upward trend in fitness, and that both the structural and the qualitative property converge in the same direction. In the third scenario here is the scenario like I was speaking about there, where once the ratio of mutation to selective pressure exceeds the fidelity significantly, what you get is this disconnected structure, where the structural trait tracks well with the fitness of the system, but the qualitative properties are completely divorced. So there's just no rhyme or reason to what you'll see in the qualitative domain, even though, say, the organism is getting taller, or whatever the structural property might be. And so that aligns with the system where knowing the set of selected structural entities told us nothing about the color that we'd be getting in the qualitative domain. And we'll be exploring this more in a future video. Finally, I mentioned it at the start, but we also need to take into account in our fidelity measures not only the translation between separate domains of S and Q, but also the transmission to higher levels of those domains. So it seems apparent that organisms are clearly not, in any sense, fundamental entities. They're composed of many levels of hierarchical structures, from tissues and organs down to cells and molecules and atoms beneath them. There's no particular reason to suspect that a conveyance on some fundamental level, say between fundamental fields and sort of primitive qualities like just flashes of some sort of sensation, on a fundamental level, even some sort of general panpsychist picture, there's no reason on its face that we should believe that that would give rise to any structured qualitative system. So on its face, these results that we were mentioning, especially the QSL, seem to favor systems with high fidelity, because if you have high fidelity between the domains, it's going to be easy for the selective pressure in one domain to convey into the other, and vice versa. If you take a structurally determined system, you're more likely to see a system like we were talking about, where there's a clear selective pressure towards certain traits in the structural domain and no rhyme or reason at all to the qualitative domain. So I kind of see that as like, just imagine that there's people walking around and there's nothing going on in their heads except for some crazy radio static of sensations that has no rhyme or reason. And I don't see any reason why that is any kind of a logical contradiction. It seems to me like it is a perfectly possible scenario, but it doesn't seem to be the scenario that we inhabit. So in actual systems, the fidelity and conveyance to higher order systems will be as significant as the fidelity between domains, and we'll be exploring different types of higher order systems sort of as illustrations and some proposals for potential models of what those higher order systems could look like. Not in any sense giving a universal or a complete set of what those possible models might be, but sort of sketching out what some potential models could be for particular mental phenomena. And then finally, this kind of goes to the points that I've been making, that without accounting for higher order systems, we can't account for the coherence of our experience with macro-sized objects. So to wrap things up, it seems that we've actually made some progress on this question in terms of a few key conclusions. The first is that any correlation between domains will convey a selective pressure between them. So there isn't any requirement for a necessarily causal connection, and we'll be exploring in a later video what would constitute a causal connection, but there's no causal connection that's required in order for a selective pressure to be conveyed between the domains, only that there's a correlation between them. So that's pretty important. Second, the selective pressure can only be efficacious under specific conditions of a minimal fidelity between the systems. So although the selective pressure will be conveyed no matter what level of correlation, even a minuscule correlation, will convey a minimal selective pressure between the domains. It can only be efficacious if the selective pressure that's conveyed is sufficient to outweigh any noise coming through in the way of random mutation. And so there has to be a minimal fidelity of that selective pressure in order to outweigh the random mutation. So what this ultimately means is that you can have a selective pressure that's efficacious in the structural system, but there is no coherent selective effect in the qualitative domain. So while an organism might be selected to keep getting larger, it would have no effect on any qualitative aspect of those organisms in any coherent way. And the third conclusion that we've come to is that just as important as the fidelity between the domains on a fundamental level are in the coarse grained into higher order systems. So in the same way that you need to take into account the fidelity conveying from a structural to a qualitative domain, you also need to take into account the fidelity conveying between levels of representation within each of those domains. And that'll be something that we'll explore pretty deeply with different model systems and so forth.